Hello everyone, welcome to this class, Organic Spectroscopic Analysis. In previous lecture, I have introduced you UV spectroscopy. In this lecture, we'll continue to learn UV spectroscopy, especially for the chromophore and substituent effects. Remember, the electrons present in organic molecules are involved in covalent bonds, or lone pairs of electrons on atoms, such as oxygen or nitrogen. Since similar functional groups will have electrons capable of discrete classes of transitions, the characteristic energy of these energies is more representative of the functional groups than the electrons themselves. A functional group capable of having characteristic electron transitions is called a chromophore. Structure or electronic changes in the chromophore can be quantified and used to predict shifts in the observed electronic transitions. As for organic chromophones, alkanes only possess sigma bonds and no lone pairs of electrons, so only the high energy from sigma to sigma star transition is observed in the far UV. This transition is destructive to the molecule, causing cleavage of the sigma bond. Alcohols, esters, amines, and sulfur compounds. In the case of simple aliphatic examples of these compounds, the N to sigma star is the most often observed transition. Alkane sigma to sigma star is most often at shorter lambda than 200 nanometers. Please note how this transition occurs from the HOMO to the LUMO state. Alkenes and alkynes. In the case of isolated examples of these compounds, the pi to pi star transition is observed at 175 and 170 nanometer respectively. Even though this transition is of lower energy than sigma to sigma star transition, it's still in the far UV. However, this transition energy is sensitive to substituents. Carbonyls, unsaturated system incorporating nitrogen and oxygen atoms, can undergo N to pi star transitions in addition to pi to pi star transitions. Despite the fact this transition is forbidden by the selection rules, it's the most often observed and studied transition for carbonyls. This transition is also sensitive to substituents on the carbonyl. Similar to alkenes and alkynes, non-substituted carbonyls undergo the pi to pi star transitions in the vacuum UV, sensitive to substitutions effects. Now let's look at the substituent effects. From our brief study of these general chromophones, only the weak N to pi star transition occurs in the routinely observed UV. The attachment of substituent groups other than hydrogen can shift the energy of the transition. Substituents that increase the sensitivity and wavelengths of absorption are called oxochromes. Common oxochromes include alkyl, hydroxy, alkoxy, and amino groups, and halogens. Generally, substituents may have any of these four effects on chromophore. 1. Photochromic shift is a shift to longer wavelengths. 2. Hypochromic shift is shift to shortened wave number and higher energy. Hyperchromic effect leads to an increase in intensity. Hypochromic effect leads to a decrease in intensity. Conjugation is the most efficient means of bringing about the photochromic and hyperchromic shift of unsaturated chromophore. These observed shifts from conjugation imply that an increase in conjugation decreases the energy required for electronic excitation. For molecular orbital theory, two atomic p orbitals formed two sp2 hybrid carbons combined to form two molecular orbitals in althane. When we consider butadiene, we're now mixing four p orbitals, giving four molecular orbitals of an energetically symmetric distribution compared to ethylene. Extending this effect out to longer conjugation systems, the energy gap becomes progressively smaller. Similarly, the lone pairs of electrons on nitrogen, oxygen, sulfur, halogens can extend conjugated systems, oxychromes. Here we create three molecular orbitals. This interaction is not as strong as that of conjugated pi system. Methyl group also cause a bathochromic shift, even though they are devoid of pi or n electrons. This effect is thought to be through what is termed hypoconjugation, or sigma bond residence. In this lecture, we have learned many chromophores and substituent effects in UV spectroscopy. Hope you enjoy it. Thank you for watching.